in quantum mechanics, we start by reading about matter waves, or the de Broglie or de Broglie, like we say, the de Broglie hypothesis. So my doubt here is that what exactly is oscillating in a matter wave? Yeah, matter waves, right? So what is oscillating? In electromagnetic waves, we know that you have electric and magnetic fields that are oscillating. Yeah, that way. That way. Yeah. So we in electromagnetic waves, electric and magnetic fields are oscillating. Yes. In gravitational waves, what is oscillating? So we're not talking about gravitational waves here. We're talking about the Broglie waves. Okay, matter waves. We not don't let's not confuse that with gravitational wave. That's a whole different thing. In gravitational waves, it's space time itself that is distorted, but we are talking about matter waves here. So let's talk about that. So what is the de Broglie hypothesis, de Broglie hypothesis, which is better known as wave particle duality? It is something Mr. No, Prince Louis Victor, whatever, the Broglie, he was a prince. He proposed this as a massive breakthrough in the 1920s. It was a massive breakthrough in quantum mechanics, in quantum physics at the time. We did not have mechanics yet. It was a bunch of jumbled, disparate experiments, and it was very, very confounding until uh, Mr. Paul Dirac came in, and Mr. Heisenberg came in, and Schrödinger came in, and Pauli, all that. Okay, I'll not go into the history of this. So the hypothesis, the Broglie hypothesis, is that particles like electrons, etc., have a wavelength. What is this wavelength? It is h divided by p, where h is the Planck constant and p is the momentum of the electron. Okay, and this wavelength of the electron, or whichever particle, fundamental particle, subatomic particle, it's associated with the wave-like nature of the particle. And then you have the concept of the wave function. So this wave-like nature of the particle is described by what we call a wave function. So that is the wave particle duality. Particles have a wave character, a wave nature, and waves also have a particle character. I mean, talk about the photon. The photon is a particle. When we talk about when it comes to certain phenomena like the photoelectric effect, you cannot explain that unless you consider light to be a particle, a photon. Yes, but when it comes to other things like the double slit experiment, etc., you have to think of light as waves. So there, and that applies to electrons as well, the same wave particle duality. So so you can have a particle, everything has a particle as well as a wave nature. That's the wave particle duality. Now in quantum mechanics, the state of a particle is described by what we call a wave function, psi. You know, psi. So what is this wave function? This wave function is a complex valued function of space and time, of x and t. And this wave function contains all the information about that one particle. So that one particle, let's say this electron that we are referring to, has a wave function. And this wave function is a function of position and time, space and time, x and t. And this wave function contains all the information about the particle. And how do we actually utilize it? We take the square of the absolute value of the wave function. It's a complex valued function. So we take the square of the absolute value of the wave function, and that gives us what? It gives us the probability density of finding the particle at a position x at a time t. So psi, this wave function psi, is not directly observable. It has no real physical meaning. The square of its absolute value has a physical meaning, and that is a probability density. So there was, when the wave function first came up, okay, when Schrödinger came up with the Schrödinger equation, there was this big debate, and everyone was perplexed as to what does this psi, this function psi, describe. And Schrödinger was of the opinion that it describes the distribution of the electric of the charge of the electron over space. That was what he believed initially, until, well, there was a revision of the understanding of this. So psi itself, the wave function, is not observable. Only the square of the absolute value of the wave function, it has a physical meaning. It is a probability density. So now the question is, what is oscillating, right? What exactly is oscillating in a matter wave? So it's not a physical oscillation. Okay, the de Broglie waves, or which are described by the wave function psi, they are not They are not like classical waves. In a classical wave, in a wave of water, you have a physical quantity. Like, let's talk about the light. So you have uh, the electric field which oscillates, right? Or in sound waves, you have pressure that oscillates, and so on. But in matter waves, it is the probability amplitude that exhibits wave like behavior. That's what it is. So this oscillation is in the mathematical sense of the complex phase. It is not a tangible physical quantity that we're talking about. Okay. So in a matter wave, it's the complex phase of the wave function that is oscillating. And this oscillation is not a physical movement of matter, but a variation in the probability amplitude described by the wave function. And yeah, you if you really want to understand this, I mean, there's no intuitive way of looking at it, right? Because quantum mechanics is completely non-intuitive. It doesn't make any sense whatsoever. You just have to get used to it. You get used to these ideas. You cannot give metaphors and examples of the real world, even though the real world emerges from the quantum world. Okay, so that's what it is. That is what matter waves are. That is what the Broglie. It's not a hypothesis. It's the wave particle duality, and that's what it means.